Hello students, in this video we are going to discuss another problem in vector space. Let us continue from the previous class. In the last class we discussed the first problem. At the end of the coefficient matrix is not invertible. If the coefficient matrix is not invertible, then the given set of vectors are not linearly independent. That is, the given set of vectors are linearly dependent. So the given vectors are linearly dependent, then the given vectors do not span R3. So in this problem, x1, x2, x3 do not span R3 because the coefficient matrix A is not invertible. So this is the final concept. So next problem, determine whether the following set S is linearly independent or not. Given set S is the collection of 2 cross 2 matrices. There are 4 matrices 1 0 minus 2 1 0 minus 1 1 1 minus 1 2 1 0 2 1 minus 4 4. So these 4 matrices are linearly independent or not. These vectors are linearly independent or not checked by the given solution. So given S equal to 1 0 minus 2 1 0 minus 1 1 1 minus 1 2 1 0 2 1 minus 1 4. So these 4 matrices, that is 4 vectors, represented by a linear combination using the scalars a1 a2 a3 a4. That is, let us take a1 u1 plus a2 u2 plus a3 u3 plus a4 u4 equal to 0. Substituting the given vectors, given matrices, we get the equation a1 into first matrix plus a2 into second matrix plus a3 into third matrix plus a4 into fourth matrix equal to 0. Then using the scalar multiplication and then matrix addition, we get 2 cross 2 matrix in left hand side. It is equal to 0. So 2 matrices are equal, then the corresponding elements also equal. So using this concept, we can write 4 equations a1 minus a2 a1 minus a3 plus 2 a4 equal to 0. Equation number 1, minus a2 plus 2a3 plus a4 equal to 0. Equation number 2, minus 2a1 plus a2 plus a3 minus 4a4 equal to 0. Equation number 3, a1 plus a2 plus 4a4 equal to 0. Equation number 4. So solving these 4 equations, we get the values of a1, a2, a3, a4. If all the values are 0, then the given set of vectors are linearly independent. If any one is non-zero, the given set of vectors are linearly dependent. So it is a rule. Let us find the values of a1, a2, a3, a4 after solving these 4 equations. Let us take 3 minus 4, we get equation number 5, that is minus 3a1 plus a3 minus 8a4 equal to 0. This equation is added by first equation, we get minus 2a1 minus 6a4 equal to 0. So from this equation, we can find a1 in terms of a4, that is a1 equal to minus 3a4. So our aim is, other than a4, a1, a2, a3, all the values are in terms of a4. We can find a1, a2, a3 other than a4 in terms of a4. Equation number 4 implies minus 3a4 plus a2 plus 4a4 equal to 0. From this equation, we get a2 in terms of a4, that is minus a4. From equation number 1, we get a3 equal to minus a4. So now we get a1, a2, a3 in terms of a4. So put a4 equal to 1, any arbitrary value, we can choose a4 equal to 1. So we get another values a1, a2, a3 are minus 3, minus 1, minus 1. So these 4 values are non-zero values. So from the concept of linearly independent or linearly dependent, here the given 4 vectors are linearly dependent because all the scalar values are non-zero values. So therefore S is linearly dependent. Next one theorem, very important theorem. Prove that the intersection of two subspaces of a vector space is also a subspace. That is a theorem. So let us take two subspaces W1 and W2 of a vector space capital V. By the result, every subspace contains a zero vector, that is 0 belongs to W1 and W2. So 0 belongs to W1 and W2, then implies 0 also belongs to intersection of W1 and W2. So from this concept, clearly W1 intersection W2 is non-empty subset of V because W1 intersection W2 contains the element 0 element. So W1 intersection W2 is non-empty. Then let us take any two elements x, y from this set, that is W1 intersection W2. So if x, y belongs to W1 intersection W2, then x, y is also belongs to W1 and also belongs to W2. So already we know W1 and W2 are two subspaces. So subspace satisfies the closure property. So therefore x plus y is also belongs to W1 and also x plus y is also belongs to W2. So x plus y belongs to W1 and also belongs to W2. Then this element is also belongs to intersection W1 intersection W2. Next let us take alpha belongs to capital F and x belongs to W1 intersection W2. So x belongs to W1 intersection W2, then implies x belongs to W1 and also x belongs to W2. So W1 and W2 are subspaces. So both subspaces satisfies the scalar multiplication. Therefore all by x belongs to W1 and also all by x belongs to W2. So from this finally we get all by x belongs to intersection W1 intersection W2. Any non-empty subset of V satisfies the vector addition and scalar multiplication under the operation capital V. Then the non-empty set is called subspace of V. So this is, it is the definition of a subspace or a condition for the subspace. So here both conditions are satisfied. Therefore W1 intersection W2 is also a subspace of capital V. So finally we get intersection of any two subspaces is also a subspace of a vector space. Next one problem. So that 1 comma x into 1 minus x is a basis of P2 of R. So we need two conditions for basis. One is linearly independent and another one is the subset generates a whole space, vector space P2 of R. Now let us check these two conditions are satisfied or not for the set 1x, x into 1 minus x. So from this problem the set is taken as capital S. Now to verify these three vectors 1x, x into 1 minus x are linearly independent or not using the scalars a, b, c. Okay, let us take the linear combination a into 1 plus b into x plus c into x into 1 minus x equal to 0. So from this equation let us find the scalar values a, b, c. So both sides equating the coefficients, we get a equal to 0, b plus c equal to 0, minus c equal to 0. So from these three equations we get the scalar values a, b, c are all 0. So from this linear combination the scalar values are all 0. By the definition of linearly independent, the given set of vectors are linearly independent because the scalars are all 0. Therefore 1x, x into 1 minus x is a basis of P2 of R. So these are all some problems and theorem in a vector space. So let us continue